Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about crystal field theory. What is crystal field theory and why it is important in inorganic chemistry? So first I will show you this color. And this color have some value 400, 500, 600, 800. What is the meaning and why the color picture is here? So you know relationship between colors and complex metal ion. Okay, so you have the dz square, dx square minus y square, dz square, you have dxy, dyz, dzx. So what is crystal field theory? You know, model explaining bonding for transition metal complexes. Originally developed to explain properties for crystalline material. What is the basic idea behind it? Electrostatic interaction between lone pair electrons result in coordination. So you have empty hybrid orbital on metal, you have filled sp3 hybrid orbital on ammonia. So dipole moment you can see from metal to ammonia, resulting molecular orbital of sigma bond between metal and ammonia. Now, you know CFT, electrostatic between metal ion and donor atom. So separate metal and ligand high energy. Coordinated metal ligand stabilize. Destabilization due to ligand d-electron repulsion. Splitting due to octahedral field. So you have energy here. Separated metal and ligands, electrostatic interaction. Third, you have the ligand d orbital repulsions. This is the metal plus coordination ligand. So you can see the differences. And the last, you see the splitting of outer d orbital in octahedral field. So you have much energy first and then separate metal and ligand, and then ligand d orbital repulsion, and then you can see again raise in chemistry atomic energy, and then splitting of outer d orbitals in octahedral field. Now crystal field theory describe bonding in metal complexes. Basic assumptions in crystal field theory. What is this basic? Electrostatic interaction between ligand and metal. D orbitals align along the octahedral axis will be affect the most. More directly the ligand attacks the metal orbital, the higher the energy of the d orbital. In an octahedral field, the degeneracy of the 5d orbital is lifted. So, you know d orbital and ligand interaction octahedral field. Ligand approach metal in different direction. On the basis of that, you have the dz square, dx square minus y square, dxy, dyz, dzx, xz. So d orbital pointing directly at axis are affected most by electrostatic interaction, so higher energy. D orbital not pointing directly at the axis are least affected, stabilized by electrostatic interaction. Now, splitting of d orbitals. You know, energy you can see d orbital is split in octahedral field. The energy gap is referred to as 10 dq or delta, the crystal field splitting energy. The dz square and x square y square orbital lie on the same axis as negative charge. Therefore, there is a large unfavorable interaction between ligand orbital. These orbitals form the degenerate high energy pair of energy level. The dxy, dyx, dxz orbital bisect the negative charge. Therefore, there is a smaller repulsion between ligand and metal for these orbitals. So these orbitals form the degenerate low energy set of energy level. So you have two sets here, one set, another set have the 3 degenerate and 2 degenerate. Here initially 5 degenerate. So magnitude of CF splitting. Color of the complex depends on the magnitude of delta. So large metal, large delta, higher oxidation state, larger delta. Just remember, this is very important for your examination. Large metal, large delta, higher oxidation state, larger delta. Ligand spectrochemical series. You know chlorine, fluorine, water, ammonia, En, NO2, N-bonded and carbon bond. Weak field ligands, low electrostatic interaction, a small CF split. High field ligand, high electrostatic interaction, large CF. You can see in this example. Less and it is large. So Cn is here. Here fluorine is here. So spectrochemical series increasing delta. Now electron configuration in octahedral field. Electronic configuration of metal ion. S electron are lost first. D3 plus is a D1. B3 plus is D2 and chromium 3 plus is D3. So what is the Hund's rule? You know very well. First 3 electrons are in separated orbital with their spin parallel. Fourth electron has choice. Higher orbital if delta is small, high spin. Lower orbital if delta is large, low spin. So high field ligand, a small delta, high spin complex. A strong field ligand, large delta, low spin complex. And that is, this slide is very important for competitive examination. Now you can see, have these 4 electrons. You have 2 types of, because 4 electron have choice, either it will here or here. So you can see, if large this one, then pairing occurs. If it is less delta value, no pairing. Now high spin versus low spin, D1 to D10. Electronic configuration for electron configuration for octahedral complexes of metal ion having D1 to D10 configuration, MH2O, if you have water as a ligand. Only D4 and D7 cases have both high spin and low spin configurations. So electronic configuration of octahedral complex of metal ion having from D1 to D10, only D4 through D7 both have the high spin and low spin. So you can see the high spin and low spin. Now color absorption of cobalt 3 plus complexes. The color sum complex of cobalt 3 plus, you can see 700 if you have the another ligand, if you have this 370. So fluorine, you have wavelength of light absorbed, higher wavelength and low energy. Here cyanide 370. So red, yellow violet, blue ultraviolet, and color of the complex, green, dark green, blue green, yellow orange, pale yellow, like this. So complex with fluoride ion is higher spin and has one absorption band. The other complexes are low spin, have 2 absorption band. In all but in one case, one of these absorption in the visible regions of the spectrum. The wavelength refer to the center of that absorption band. Now color and how we perceive it. You can see artist color wheel showing the color which are complementary to one another and the wavelength range of each color. So black and white. When sample absorbed light which we see is the sum of the remaining color that strike our eyes. So if sample absorb all wavelength of visible light, none react our eye from other sample. Consequently, it appears black. If sample absorb no visible light, it is white of color. So my friends, you can see absorptions and reflections. If the sample absorb all but orange, the sample appears orange. So further, we also perceive orange color when visible light of all color except blue strike our eyes. In a complementary fashion, if the sample absorb only orange, it would appear blue, and blue orange are said to be complementary color. So you can see in this picture. So light absorption properties of metal complexes. Recording the absorption spectrum, you have the source of visible light, you have slit here, you have narrow beam of polychromatic light, you have prism here, and then monochromatic, and you have the graphical display of a spectrum like this. So complex influence on color. compound of transition metal complexes solutions. You have seen this is the colorless, this is blue, green, and so you have different compounds here. So color absorption of cobalt 3 plus complexes. You know color of some complex of cobalt 3. I already show you. Now octahedral, tetrahedral and square planar splitting. So this is the splitting of octahedral. In a square planar you see 1, 2, 3, 4. Here only 2. So here dz square come down and dx square minus y square. Now here dxy is go up. So this is the splitting. So here again the reverse of this. So del in tetrahedral and high spin, delta high spin. So mostly D8 system, majority low spin, a strong field ligands. It is palladium 2 plus, platinum 2 plus, iridium plus and gold 3 plus. So in summary, crystal field theory provide a basis for explaining many features of transition metal complex. Example in chloride transition metal complex are high color and why some are paramagnetic while other are diamagnetic. The spectrochemical series for ligand explain nicely the origin of color and magnetism for this compound. There is evidence to suggest that metal ligand bond has covalent character, which explains why these complexes are very stable. So my friends, the molecular orbital theory can also be used to describe a bonding scheme in this complex. A more depth analysis is required. So in our next video, we will discuss further about this theory. So if you like this video, then subscribe my channel, share it in your friend circle, and at last I would say thanks for watching.